Section 10.2, I'm going to do some free body diagram analysis for objects undergoing circular motion. In this example, we have a wrecking ball that swung from a cable. We're to neglect drag. Part A wants us to identify the forces on the wrecking ball, including their direction. So the wrecking ball will have its weight acting down. That's the force of gravity from the Earth. And the wrecking ball is attached to a cable, so there will be a tension force that acts along the cable away from the object, and in this case, that's going to be up. In part B, we're to compare the magnitudes of the two forces. So prior to learning about circular motion, you might have looked at this situation and say, well, the cannonball is not moving up, it's not moving down, therefore the forces in the up and down direction must be in balance. But they are not going to be in balance because in this situation, the wrecking ball is undergoing circular motion. And if it's undergoing circular motion, there must be some net force that acts towards the center of the circle. And at this position, up is towards the center of the circle. This is going to be the direction of the net centripetal force. That net centripetal force, which points towards the center of the circle, is going to equal the tension minus the weight. And the net centripetal force has to be a positive value. In order for this to be a positive value, the tension force has to be greater than the weight force. And this is going to be true for all situations involving an object in circular motion. The total force inwards must be greater than the total force outwards. Let's look at another similar example. Here we have a skateboarder that rides into a valley. We're neglecting drag, and we're going to draw a free body diagram showing the forces on the skateboarder. Well, the skateboarder has weight. The skateboarder is in contact with the ground, so the ground will exert a normal force upwards. And again, we are going to compare the magnitudes of the forces. Well, it's important that we picture where the center of the circle is, which might be somewhere like that. And that means that the centripetal direction at this position for the skateboarder is up. And that net centripetal force has to be directed up. If we add up the forces to calculate the net centripetal force, we have to end up with a positive value. In order for us to end up with a positive value, the larger force has to be the normal force. Again, there has to be a greater total force acting centripetally than the total force that is acting centrifugally outwards away from the center of the circle. All right, slightly different problem here. Here we have a car that's driving over a hill. We're going to draw a free body diagram showing the forces acting on the car. Car has weight, and the car is in contact with the road that will apply a normal force up. Now, what's different about this one is the center of the circle is located underneath where the car is. So in this case, the centripetal direction has to be downwards at this car's position. And when we add up the forces to find the net centripetal force, in this case, we're going to take the weight minus the normal force. And again, the weight has to be the greater of the two forces because the weight is acting centripetally, and there has to be a larger force acting centripetally than the forces acting centrifugally. There has to be a larger force in than out. All right, one more example. Here we're going to have a car that's driving around a circular track, and we need to draw a free body diagram for the forces acting on the car shown in the rear view. So we have two pictures of the same event happening here because it's very hard to draw the forces that are acting either into your screen or out of your screen in that third Z direction. So we're gonna draw two sets of forces. It's the same event happening, but it's just shown from two different perspectives. So from the rear view, we've got the weight acting down and we've got the normal force acting up. In this case, there is no motion in the y direction, and so we should know that the normal force is going to equal the weight of the car. The car is moving in a circle, so there has to be a force that is pulling the car towards the center of the circle. And from the rear view, we have here the center of the circle is to the right, so there has to be some force acting to the right, and in this case, it's going to be the friction from the road. Assuming that the car's tires are not slipping on the road, that's going to be a static friction force. And we're going to spend some time in the next unit, or the next section rather, talking about how we can calculate that static friction force and what maximum speed might the car be able to go around this turn. From the top-down view, we're going to have that sideways friction. Now that's the friction, that's the purple arrow that we drew for the rear view of the car. There's also going to be some forward friction, backward friction, and drag. And usually we're not going to worry about the forward friction, the backwards friction, and the drag, because typically we're going to assume that the speed of the car is constant. And so we're not really going to have to talk about these forward and backward forces. If the speed of the car is constant, those forces are going to end up canceling, and the forward friction is going to have to equal the sum of the drag and the backwards friction in order for the car to maintain a constant speed.